All right, great. So hello everyone. I'm Keaton Kapse, and I'm going to be presenting today's reading group along with Christopher Wellington. So our reading group today is on Fourier-Net Plus. I'll start with the introduction, and Christopher will continue with the demo and what we've learned. So beginning with the introduction, um, the first question that or the basis of this presentation is on medical image registration, and we need to know what medical image registration is. So medical image registration is also known as medical fusion or medical image matching. It is the process of learning spatial deformations, which are needed to establish the correspondences between a fixed image and a moving image. So, like basically, its goal is to find an optimal spatial transformation that like best relates to the underlying anatomical structures of like some medical image data. It is often used in clinical applications like segmentation, dose accumulation, image reconstruction, and so on. And like it is categorized into multiple factor, like it's categorized on the basis of multiple factors, which can include data dimensionality, image modality, registration basis, and optimization techniques. Um, Current academic focus, like for the past 2 decades or so, in this field has been on intensity-based deformable image registration, wherein given a moving image and a fixed image, the goal is to compute a dense deformation field or a DDF that maximizes the similarity or like the distance between the two input images. The goal can seem simple, but in practice, constraints and assumptions regarding smoothness, symmetry, and topology are opposed before the deformation is actually computed. And like, well, they basically serve as recurralization terms, and the application of these terms lead to solutions that are not of unique. There are multiple approaches to medical image restoration, well, with three of them being the most commonly used. They are iterative, deep learning, and hybrid approaches. Iterative optimization techniques, they include freeform deformation or FFDs, LDDMMs, ANDs, and Flash. These techniques are quite widely applied and are extremely mathematically sound, but they require a lot of hyperparameter tuning for each of the image pairs, and they can be quite computationally expensive as well. Deep learning approaches, they are the most common of the three, and they often rely on their ability to perform fast inference and can use external information such as like anatomical masks during training. The most effective methods like voxel morph over here, they typically employ units to estimate the DDFs, and other neural network models can try to enhance the registration performance by using units in a cascading style, and they often replace convolutional blocks with more complex layers like sometimes attention-based transformers and parallel convolutional blocks. But these models usually come up with like they're quite complex and have more number of parameters, and like they have an additional overhead of like more number of multiply and add operations, which can negatively impact training and the efficiency in the inference. And the hybrid model is like the least common of the three, and it basically, as the name says, combines iterative approaches with deep learning. Um, as I said, almost all deep learning based registration approaches utilize units. The authors of the Fourier-Net paper suggest that it may not be necessary to include the entirety of the decoder path in the units, and training and like efficiency of those models can be further improved by making them learn on a low-dimensional representation of the displacement field in the band-limited Fourier domain. So as you can see in this image over here, the top row is like the original moving image, fixed image, and the displacement field and the deformation field that we got from them. While the bottom image, the bottom row, it shows that these are the coefficients that we get from the band-limited Fourier domain. And it shows that just these few coefficients are necessary to get a full resolution reconstruction of the displacement field in like with a high accuracy, basically. So what the Fourier model is doing is like it's learning such a representation of the displacement field. And after the authors removed several layers from its unit part, the model outputs only the low frequency coefficients in the displacement field, and a decoder network in the model then reconstructs the full resolution displacement field using the coefficients with the help of some zero padding layers and an inverse discrete Fourier transform, or an IDFT layer, basically. And also both of these layers, the zero padding layer and IDFT layers, are parameter free. So they have a positive impact on the running time of the model. And here you can see this is the architecture of the Fourier-Net model. The convolutional network in the encoder first produces a low-dimensional representation of the image pair, like the displacement field, basically, followed by an embedded DFT layer that maps the low-dimensional representation into the band-limited Fourier domain. In the decoder part, which consists of the padding and the IDFT layer, along with some optional squaring and scaling layers, reconstruct the displacement field to its full resolution. And like, well, then it's the warping layer deforms the moving image and the loss is computed, basically. The Fourier-Net model is actually quite similar to the Fourier-Net plus model is quite similar to the Fourier-Net model, except for one major difference, which is like there is the presence of a model-driven encoder, which converts the full resolution image pairs into their low-dimensional representations, which are then fed into the convolutional network. And the ConvNet consists of some 3D convolutional computations, which are like quite expensive. But since we are using low resolution representations, the overhead is quite significantly reduced. And well, then after that, basically, the model is same as the Fourier-Net model. Well, one disadvantage of using the Fourier-Net plus model is that it is a lighter model compared to the Fourier-Net model, and it can sometimes not accurately capture all of the details in the deformation field. So to mitigate that, we can use multiple Fourier-Net plus models in a cascading style, so that all of those features get captured perfectly. And now Christopher will talk about the demo.
Cool, thank you. So this is a demo of the Fourier-Net model and a couple of random images. So the input is a pair of stacked images, a moving image and a fixed image that gets sent to the encoder where the DFT happens. And then once that happens, then the limited band is sent to the decoder, which the IDFT happens, and then the squaring and scaling. And then what is output is a low-dimensional spatial representation of the image. Next slide, please. So these are the randomly selected images that we used in the code. One is a moving image and the other is a fixed image. And there's also a difference map of the difference between the moving and fixed images. Next slide. So here's a plot of the band limited displacement. So instead of using the original high resolution images of the fixed and moving images as input for the network, the authors utilized a band limited representation of these images. To achieve this, they first transformed the images into the Fourier domain using the discrete Fourier transformation layer, and then crop the resulting data to extract low frequency signals and send that to the decoder. So these low frequency signals are in complex valued Fourier space. So a inverse discrete or inverse DFT operation is applied to convert them back into the spatial domain, resulting in a new spatial patch, which represents the image in band limited form and used as input for the convolutional neural network. Next slide, please. So here's a plot of the deformation grid, which indicates the changes that were made during warping. So a smoother deformation grid would indicate that less changes were made and more deformations, and then less smoothness indicate more changes were made. Next slide, please. So now we have a plot of the warped image. So we could see the original moving fixed images, and then also the diff before and diff after, which was sent to the convolution net. And then once they were sent through the decoder, we now see what the warped image is. Next slide. And so you can access the code that we used on this GitHub link for the live demo. Next slide. Okay, now what we learned. So here is a visual comparison of the different methods from the paper, and notice the changes in the deformation grids for the different models. How Fourier-Net is very smooth compared to like voxelmorph or the other methods that were used. Next slide. So the recommended practices by the authors, the impact of the embedding in DFT layers affects computational efficiency and performance, which that indicated as a very necessary to use in the Fourier-Net. And without those DFT layers, you end up with just a regular old neural network, which takes more computation time than the Fourier-Net. And then also using a band limited representation is more effective than using a low resolution downsampled displacement field, which resulted in a lower performance when compared to the two. And also lower resolution images achieved faster computation time, but the result was in lower performance as with the resolution band limited images. So depending on how much performance you want, you have to sacrifice time. And so it's up to the user to decide which they want to go for, faster time or better performance. But the addition of cascades in Fourier-Net and diff Fourier-Net plus improved the registration performance on both the 2D and 3D IXI datasets while maintaining computational efficiency, making them competitive with full resolution UNet and diff UNet models, which is huge because, as we heard before, the UNet and diff UNet models would take a much longer time than the Fourier-Net. Next slide. So in conclusion, the study introduced Fourier-Net, Fourier-Net plus, and a cascaded Fourier-Net plus to enhance the efficiency of the UNet style registration networks by learning the displacement and velocity fields in the band limited Fourier domain from low resolution images. The methods demonstrated significant computational savings while maintaining competitive registration accuracy across the datasets. However, they assumed that the displacement and velocity fields lack high frequency signals, potentially affecting the performance in complex tasks. However, Fourier-Net plus efficiently addressed that issue with even in tasks like brain registration by removing the high frequency image information in the encoder while still maintaining performance. All right, next slide. Cool, and that's everything. There's the GitHub link and the link to the paper. And if anyone has any questions, we are available to answer them.